Raw data is inherently disorganized. Data scientists use polynomials as dynamic modeling engines to translate physical and economic constraints into computable logic. To manipulate these models, we must track their complexity. In algebra, that complexity is defined by a polynomial's degree, the value of its highest exponent. Multiplying polynomials sums degrees. M and n become m plus n. Dividing subtracts them to m minus n. Adding caps the degree at the highest exponent, the maximum of m or n, unless leading coefficients cancel, dropping the system's degree. By mastering these rigid parameters of degrees, we can safely translate real-world constraints into organized algebraic systems. These algebraic rules apply directly to physical space, allowing us to translate geometric boundaries into predictive volume models. We begin with a physical constraint, a flat rectangular sheet measuring 5 feet by 3 feet. To construct a box, we must cut identical square corners of an unknown size, x. Removing those corners alters the width of the sheet. The original 5 feet is reduced by x at each end, creating a new width of 5 minus 2x. The same mathematical constraint applies to the length, where removing 2 squares leaves us with a boundary of 3 minus 2x. Folding these flaps upward into a three-dimensional shape turns the cut size, x, into the box's final vertical height. To calculate the volume of this container, we apply the formula length times width times height. By substituting our algebraic dimensions into the formula, we create a function that models the box's volume based on the size of the cut. Multiplying these terms requires expanding the binomials to capture how the three dimensions interact. The expanded terms consolidate into a single polynomial function, 4x cubed minus 16x squared plus 15x. This resulting function is a degree 3 polynomial. Multiplying 3 independent x terms, one for each dimension, naturally creates an x cubed term. In this way, the cubic degree of a polynomial perfectly reflects the three-dimensional physical reality of the volume it models. This logic scales to massive industrial systems, where data scientists must aggregate multiple data streams into a single evaluative equation. In a manufacturing scenario, a company might operate 3 distinct processes, each producing industrial waste at different polynomial rates. The raw data is represented by 3 separate equations for waste processes A, B, and C. To find the systemic waste, we sum the polynomials by aligning their coefficients by degree. All x cubed terms are added together, followed by the quadratic and linear terms. This results in one unified polynomial representing the total waste output of the entire factory. Plugging a real-world input, such as 1,500 kilograms of raw material, into this master equation allows for the immediate calculation of total operational overhead. This same aggregation method applies to business viability, where analysts plot the combined profits of multiple product lines over time. This graph shows the curve of a total profit polynomial, x cubed plus x squared minus x minus 1. The primary goal for a business modeler is to locate the break-even point, where the company's profit is exactly 0. To find these points, we set the equation to 0 and factor the polynomial down to its core roots. The factored equation reveals the specific intersections, x equals -1 and x equals +1. Unifying nonlinear data streams into a single polynomial allows us to pinpoint operational thresholds that would otherwise remain hidden in raw datasets. Sometimes we must evaluate a system where the internal mechanism is unknown. We can observe the inputs and the outputs, but the algorithm remains hidden. We define this hidden system as a quadratic model, ax squared plus bx plus c, where the coefficients a, b, and c are the parameters we need to solve. To reverse engineer this system, we use the remainder theorem. The output data provides our first constraint. When the unknown system is divided by x, the remainder is exactly 1. The remainder theorem states that evaluating the function at 0 must equal that remainder. This causes the quadratic and linear terms to collapse, proving that the constant c is 1. A second output shows that when the system is divided by x minus 1, the remainder is 7. This means the function evaluated at 1 equals 7, which we translate into a linear equation, a plus b plus 1 equals 7. Finally, dividing the system by x plus 1 leaves a remainder of 1. Evaluating the function at -1 gives us our second linear equation, a minus b plus 1 equals 1. By organizing these constraints, we have constructed a clean system of linear equations from external output data. Solving this system reveals the hidden parameters. Both a and b are 3. The internal architecture of the model is now fully defined as 3x squared plus 3x plus 1. The remainder theorem allows for the reconstruction of a system's internal parameters using only its interaction with the environment. We have moved from the abstract rules of degrees to the practical mapping of physical space and the synthesis of industrial data. Polynomial operations provide the structural logic required to organize complex systems. Tracking degrees allows us to predict how complexity scales during multiplication or remains bounded during addition. Even when internal coefficients are hidden, they can be logically deduced by observing how the function responds to specific inputs. These mathematical properties are essential for building scalable, predictable models in data science. Whether the task is optimizing a physical container or reverse engineering a hidden algorithm, success relies on this level of mathematical rigor. The polynomial remains a foundational architecture for data science, allowing for the precise organization of complex variables into a single functional model.